Hey everyone, welcome to today's session on probabilistic mixture models. So, if you ever looked at messy data and thought, I bet there are hidden groups in here, so then this is for you. We'll look at the concepts, the math, and even code it up so you see how it works in real life, right? So, now we'll look into it. Okay. So here is our roadmap, and now we're going to discuss about the why we even need mixture models and what they are, and break down their key components and understand the role of latent variables and our hidden MVPs, and also look at different types and when to use them. Also, walk through the EM algorithm that powers them, and we'll see real world applications and finish with a Python demo using Gaussian mixture models. Sounds good, right? So let's go. So yeah, why mixture models need? So imagine you're the principal of a school and you plot the heights of all your students. So the chart doesn't look like one smooth hill, right? So number of students have a number of heights. So instead, it has bumps and all. So now, without me telling you anything else, what could those two bumps represent? Maybe one for boys and one for girls, right? So here is the catch. We never had the gender labels in our data. But from just the heights, we suspect that there are two hidden groups. So, and this happens everywhere in real data sets like customers, medical data, and traffic. So, these patterns, the mixture models, are statistical way of saying is I know there is more than one pattern here, but now let's find them out. So, what is probabilistic mixture model? Okay, so what is a mixture model in plain English is think of it like your data is a smoothie. So it's not just one fruit, like it's a blend of several fruits, where each fruit is a probability distribution and the smoothie is your observed data. So mathematically, we say your data comes from a weighted sum of these hidden distributions. And instead of saying this data is 100% of banana or 100% of strawberry, mixture models say. So this data is 70% of strawberry maybe and 30% of banana. So that soft clustering was like, and it's much more realistic than hard clustering like K means when you forced into exactly one bucket likewise. So here is the expression for the probabilistic mixture model, which is P of x equal to sigma k to the k equal to 1 pi k pk of x by tk theta k. So now we'll move next. Now we'll know the anatomy of a mixture model. Here is what makes up a mixture model. So here we can see K is the number of components, and here P of x by theta k is the mixing weights, and pi k is the component distribution, and theta k is the component parameters. So here, so mixing weights is something basically how much your smoothie is each fruit, and this component distribution is something like the probability distribution for each group. And for example, like we have so many like Gaussian multinomial and all, and the theta parameters like the mean and variance of this Gaussian. So in our smoothie analogy, where we talked earlier, K is like the number of fruits, and here pi k component distribution is like how much each fruit is there, and where theta k is like the exact sweetness or tartness, etc. So that is how we evaluate. So now the latent variables, where the hidden truth. So there's one more secret ingredients like this latent variables we call technically. So these are like invisible labels telling us in which group created each data and each data point. So we never actually see them, but the model learns them. So and it doesn't just say you are in a group A and it says like you are 80% in A and 20% in B. So that's why we call it soft clustering, where we can't figure it out where exactly it is and how much exactly it was there. So now we'll move into types of mixture models. So here we have few types of mixture models. One is Gaussian mixture model and multinomial mixture model, and another one is Poisson mixture model. So coming to the Gaussian mixture model is for the continuous data like heights and arrival times. Where multinomial mixture model is for like categorical or text data, like guessing an article is like 60% politics and 40% sports, likewise. And where Poisson mixture is for like counts, like number of cars passing through an intersection per hour. So this is how um, these were defined: the Gaussian, multinomial, and the Poisson mixture models. So now we'll see how it works. Here, the expectation maximization, which we called EM algorithm. So the EM algorithm is how mixture models learn. Here we have three steps. The first step is E step, which is based on current guesses and estimate how likely each point is belong to that each group. And step two we call M step. And in this, the update the group definitions based on those probabilities and will repeat until nothing changes much as we got the correct likely input value. Then it's like sorting puzzle pieces, like guess where they go, fix the picture, or guess again until the image is clear. So until we got the correct one, we'll repeat those steps. Okay. Next, why choose mixture models? So why we use them is because they handle overlapping clusters beautifully. Like even the data which is overlapping also, it will find out very easily. Then they give probabilities, like not just yes or no labels. They give clear probabilistic values. Then high flexibility, and they adapt to many data types, and also they can even generate new realistic data. So this is why we choose mixture models. Next, so we'll wrap it up. So mixture models are like there you go to, for example, a tool when you suspect multiple patterns hiding in your data. So they find those patterns using probabilities and the EM algorithm. So and they work in countless real world situations from school heights to market segmentation. So next, let's see them in action with Python. We have a collab, so we'll look into it now. Now we'll look into the technical part in this collab. In first step, you can see we have installed the required libraries. First, we install two libraries, which is skitlearn, matplotlib. So skitlearn is for the machine learning part, and the matplotlib for the visualization. So this quiet is just a flag, just hides extra installations messages, so our output stays clean. That's it. And then in the second part, we've also imported few more libraries, which are NumPy, matplotlib.pyplot, and From sklearn.mixture, we have imported Gaussian mixture. So numpy is for handling numbers and arrays, and here the matplotlib.pyplot is for plotting, and the Gaussian mixture from sklearn is which is ready-made class that implements the Gaussian mixture model for us. So next, yeah. So here we have also taken this, which is this line sets random seeds so that every time we run the code, we get the same random numbers. So this makes the results reproducible. That's it. Here we have also taken the data from two Gaussian distributions, which is data 1, 200 points from a Gaussian mixture distribution with a mean of 5 and with a standard deviation of 1. This 5 represents the mean and this 1 represents the standard deviation, and this 200 points is from the Gaussian distribution. So then the data 2 also had 300 points from a Gaussian distribution and with a mean 10 and standard deviation of 1.5. Think of these as hidden groups in the data set. Okay. Now this line. So here we have combined the data set and reshaped from sklearn. I combined both data 1 and data 2 data sets, and then in the single array X, and with a reshape it into a column vector because sklearn expects 2D input, right? So even if we only have one feature, we have made it like this. Then in step 4, fitting the Gaussian mixture model. So here I created a Gaussian mixture model object which is GMM, and tell it to find the components, two components. And because we know we have two groups in our data, right? Data 1 and data 2. So then fit of X, which means trains the model, it estimates the means and standard deviation and mixing weights for each Gaussian distribution. Okay. So now in the step 5 we have did here we have taken predict proba, which is proba here defines predicting the probability. Okay. Then labels. So here predicting the probability gives a soft clustering, the probability of each point belonging to each cluster. Okay. Then this predicts the gives a hard clustering, which is labels the most likely cluster for each point. For example, think of it like a point might be 70% in cluster and 30% in cluster 2. So, but predict will just assign it to a cluster 1. Understood? Then in step 6, yeah, we have printed the learned parameters. So means, which is the center of each Gaussian, and standard deviations are how spread out each Gaussian is, and the mixing ways, the relative importance of each Gaussian in mixture. Then, if you see this, the X vals, it creates 1,000 evenly spaced points between the smallest and the largest values in our data. So here. The score samples, you can see GMM dot score samples. The score samples gives the log of the probability density for each point. We exponentiate it to get the actual probability density function. So yeah, next now we'll make it a histogram of our data, so it will be uh, easy to identify, and then so it makes it a probability density histogram. So it can be compared directly to the GMM curve. Then here the PLT dot plot, which then we plot it and the red GMM curve on the top, and this shows the combined probability density from both Gaussian components. We'll run this so you'll get understand. So we also said here you can see blue and all, right? So dashed lines. So then we draw dashed lines, blue vertical lines at the means of each Gaussian. So these mark at the centers of two clusters. So then we are plotting it and labeling it. So we'll see by running the code. 1 minute. Yeah, you can see here components 2 and the random state it is taking every time 42 because we have taken here 42. Okay. So here we get the means and the standard deviations of two data and the mixing weights of two data. And here we also got the model fit histogram. So this shows the combined probability density from both the Gaussian components. Okay. So these blue vertical lines that are at the mean of each Gaussian. So these marks as the center of two clusters. So this is the data histogram, and this red line is the GMM fit, and this blue dashed lines are the mean. Yeah. So this is how uh, we'll do it practically. Hope you guys understood it, and thank you for watching.